Well, hello everybody. I hope you can see me and hear me. Coming live from Berkeley, California. Yes, it works. Let me just check, just to be sure. Do you get the sound? Everything okay? Are we live? Let me just plug in my computer so that it doesn't, I don't lose power. All right, I'm ready. So let's do it again. Well, hello everybody from Berkeley, California. Coming to you live, Edward Frenkel, mathematician, professor at Berkeley. I'm doing a live session today for the World Science University, World Science U, on the topic of my masterclass about mathematics and its connection to nature. Mathematics is a language of nature. So thank you everybody for joining. I received a number of questions from you, and you can still send me more questions at the email address, which you can find very easily, but I can tell you what it is one more time. Let's see. It is askwsu@worldscienceu.com. So askwsu@worldscienceu.com. So it's a little weird because I cannot see or hear you, but you can see and hear me. So if you want to if you want to ask me a question, you have to send an email, and then the good folks at World Science U will transmit them to me. Okay, but to start, I would like to address some of the questions which I have already received from some of you. And so here's a question which one of the questions which I have received. And so Julius, for example, Julius asked me, and thank you very much for this question. You spoke of the Langlands program unifying the continents of mathematics as being analogous to the unification of fundamental forces of physics. If the continents are unified, would this contradict Gödel's incompleteness theorem? In other words, would this imply the theory of symmetry underlying the continents would have to be complete? It's a very good question, and actually I'm glad that you brought up Gödel's incompleteness theorem, because I think this is one of the most important results discovered in mathematics in the 20th century, which perhaps is not sufficiently appreciated, and not only by the public at large, but even by professional mathematicians, because we we are aware of it, we know about it, but we try not to think about it too much because it's kind of a little bit unsettling. So let me say a few words about that. Gödel proved that there are certain inherent limitations in mathematics in the following sense, that you cannot expect to obtain all the true statements of mathematics within a finite sort of formal system. Within a system, by formal system I mean a finite number of axioms and the standard rules of inference, standard logical rules of inference, and then starting from those axioms, producing new theorems, and then new theorems deriving from the ones you have already derived, and so on. So you use all the formal structures that you have, and you try to get all the possible statements. So what Gödel has shown is that if such a formal system is sufficiently complicated, not too complicated, for example, it should contain the axioms of arithmetic. So this is a system of axioms which sets up those usual rules of arithmetic which we use. So if you have a theory a formal system which contains the axioms of arithmetic, then it's sufficiently complicated. Therefore, that's what it means. Then there will actually be a true statement which cannot be proved within the system. Now, it doesn't mean that this is somehow, it doesn't mean that necessarily it's a contradiction or it's a problem that cannot be circumvented, because if you have such a statement, you can then just add it as an axiom. So you get a new formal system, right? And then within that formal system, that will be a true statement, will be a theorem, right? It actually will be an axiom. However, by enlarging the set of axioms, you obtain a new formal system. And then in this new formal system, there will be something else. There will be another statement which will be true and yet not provable within that formal system. So it's like a horizon line, you know. We try to get closer to it, but then it moves away from us. So it's kind of a similar situation. So what it shows to me is that the process of discovery of mathematics is really an infinite process. We cannot expect somehow to come up with a finite set of axioms, and then everything will somehow follow from it. If this were the case, you might argue that mathematicians could just lose their jobs, because you could just have a computer which would be automatically producing more and more theorems from those axioms. So then it would mean that all we mathematicians need to do somehow is just to, come up with the right set of axioms, and after that we can all quit our jobs and go do something else. Well, what Gödel's incompleteness theorem tells us, that's not going to happen. It's not going to happen. So human intuition, human insight cannot be fully replaced by an algorithm, cannot be fully replaced by a computer. This is my take on Gödel's incompleteness. This is one of the things that it means. Now, but I think it's a positive thing. It's a very much a positive thing, in my opinion, and not just because it means that I will not lose my job, in the near future. But rather, is because it also shows that mathematical discovery is not really a kind of an algorithmic process. There is something more to this. And when you are a mathematician, you actually realize that, because, of course, we prepare for our work, we prepare for making those discoveries. We work, we think, and so on. But and even Einstein talked about this, that, sometimes he would work and think for a long time and so on. But then you wouldn't get it, you wouldn't see it, you wouldn't see the solution. And then he would just sort of go for a walk, and whistle and kind of try to clear his mind. And that's when, he would be hit by an idea, an insight, an inspiration. So insight, inspiration are essential components of mathematical work, of discovering mathematics. So I think it's all connected. But now going back to the Langlands program. So in my master class, as many of you have probably already seen parts of it, or perhaps the whole master class. So you know what I'm talking about. The Langlands program is one of the biggest ideas, in my opinion, one of the biggest ideas that have come out of mathematics in the last 50 years. And its goal is to connect different parts of mathematics. Okay, and for example, in my masterclass, I talked about connecting number theory and harmonic analysis. I also talked about I touched upon connecting those subjects to geometry and even to quantum physics, right? So, but we're not when we say that we're trying to connect these things. So going now more closely to Julius's question, when we say that we are unifying these things, it doesn't mean that, again, we're not trying to say that we can somehow solve all the problems that could possibly arise in mathematics, that we can prove every true statement. So therefore, I don't see that I don't see any contradiction with Gödel's incompleteness. The only way we would be contradicting Gödel's incompleteness if we were to say that we would actually find this perfect system of axioms, which would somehow unify everything, and so that from that point on, everything could be just derived by an algorithm, by a program. But that's not the case. And in a sense, even today, what I find most striking about the Langlands program is first of all, of course, that the depth of the ideas and the originality and kind of like the surprise, the unexpected, the element of surprise that suddenly problems which look to be so far apart, they come from completely different, domains of mathematics, they suddenly turn out to be related. But what I find even more striking is the fact that it's been almost 50 years since these ideas were first formulated by Langlands. In 1967, he wrote that famous letter to André Weil, in which Langlands laid out these ideas. And yet, we still don't understand the crucial points. We still don't know why there should be such a connection. You see, so the connections have been proved in many cases. In my book, Love and Math, which I mentioned in my masterclass, I describe in detail some of those connections that have been proved. And one of those connections, in fact, is related to, Fermat's last theorem, that Shmurta-Yamovey conjecture, who's proved by Ken Ribet, and then by Andrew Wiles and Richard Taylor, allowed us to have a proof of Fermat's last theorem. So some of these things have been proved. But even if we have proved some instances of the Langlands correspondence, we still don't know why. Why is there such a bridge? So, for example, one of the aspects of the Langlands program is this appearance of the Langlands dual group, which I talk about in later chapters of my book. And to me, this is still a mystery. It's still a mystery. So, in some sense, we are not really even close to understanding yet. We're not at the, it's not the end. We're not at the end of the Langlands program. If anything, we are at the beginning. We are at the beginning of the Langlands program. So the major questions, the most important questions, are still open. So that would be my question, my answer to your question. And so Michael, I just received this question from Michael. He says that he is taking a first course in representation theory, and he says, I love it. Great. Very happy to hear that, Michael. Keep pushing. And Michael asked, can you please talk more about some open questions in representation theory and how it relates to other things? Well, so first of all, maybe I should, for the benefit of some of the audience, perhaps explain a little bit what we mathematicians usually mean when we talk about representation theory. Because, of course, the word representation, it has so many different meanings. Well, in mathematics, representation has a very specific technical, concrete sense. And representation theory is about representing groups. And so one way to think about this is in terms of groups of symmetries, which I talk about in detail in my masterclass and also in my book. So for instance, I talked about how you can have, if you have a bottle, you can rotate this bottle around the axis, kind of the central axis, right? And so these are kind of the symmetries of the bottle. Whereas if you had a square bottle, you would only be able to rotate by 90 degrees and multiples of 90 degrees, right? So these are the symmetries. So this leads us to this notion of a group. A group consists of all possible transformations of a given object. So that would be a group of symmetries of that object. So in the case of a bottle, as I explained in my masterclass, this group is the circle group. Its elements can be viewed as points on a circle, because if you mark a point on a circle, any other point corresponds to a particular angle between the mark point and this point. So rotations correspond to angles, and those can be mapped as points on a circle, right? So here's an example, the circle group. Now, what would be a representation of a circle group? Well, you could say, well, this is already a representation. Rotating a particular bottle is a particular representation, which is true. But a bottle is kind of is not a mathematical object. It's a nice object because I can drink from it. But it's not a mathematical object. So instead, we modify it slightly, and so we consider we realize symmetries, say rotations, not on a concrete object like a bottle, but we realize them as symmetries of a mathematical object. And more concretely, we usually talk about so-called vector spaces. So what is a vector space? Very roughly, just a vector space is something like a line or a plane or three-dimensional space, which we observe around us. So, for instance, there's a whiteboard behind me. You can think of it as a two-dimensional vector space. Okay, and so if you have a rotation, you can think of rotation as a rotation of a bottle, but you can also realize any rotation as a rotation of a plane. Of this, you could imagine rotating this whiteboard. Well, it's fixed on the wall, so I can't really do this, but you can imagine. Actually, let me try. Let me see if I can actually show you something on my whiteboard. So, if you fix a point in here, Okay, so then you can imagine rotating, say rotating the whole whiteboard by 30 degrees counterclockwise, and likewise by any angle. So this way you realize every rotation, every element of the circle group, you realize it as a transformation of this whiteboard. The nice thing about the whiteboard is it's sort of, imagine this whiteboard extending to infinity in all directions. So this is what we call a vector space. And the representation theory is about finding ways to realize a given group of symmetries. For example, the circle group, realize each element of that group as a transformation, like a rotation of a particular vector space. So here we have found a two-dimensional representation, you see. We have found a two-dimensional representation of the circle group. You see, so but the circle group is really one of the simplest possible groups. So in some sense, there are not so many representations. This two-dimensional representation is really the basic, the most important representation of the circle group. But there are other groups as well, right? So there are more complicated groups. For example, you can think of a group of rotations of a sphere. I should have brought like a basketball or something to my office. I don't have one here. But if I had one, you could imagine. But just imagine, you know, a basketball or volleyball or something, and so or a globe, and you can rotate it in with respect to any axis which goes through the center, right, by any angle. So the group becomes much more complicated. It's not just one angle, but it's also a choice of axis of rotation. And there are many different axes. You can imagine many different axes, right? You can rotate this way, and so on. So this becomes a bigger group. In mathematics, it's called SO3. We talked about this. I talked about this in my master class. So this group already has many different representations. So in fact, it turns out that it has representations. It has an actual three-dimensional representation, because just by definition, because your ball, your sphere, you know, the surface of the basketball is embedded in a three-dimensional space. So instead of thinking of rotations of the sphere, you can think of rotations of the entire three-dimensional space. What do I mean by three-dimensional space? Just the space around me, around us, right? We live in the three-dimensional space, or we observe the three-dimensional space. Maybe there are some extra dimensions. I'm not talking about that right now. So, okay, so there is a three-dimensional representation. But in addition, in fact, it turns out there is also five-dimensional representation. There is a seven-dimensional representation, nine-dimensional, so on. For every odd number, there is a representation of that dimension. That is a vector space of that dimension on which you can realize every rotation of a sphere. This is not obvious at all. This is the beginning of representation theory. And then you can consider even more complicated groups. For example, this group SU3. So SO3 means special orthogonal group acting in three-dimensional space. Orthogonal means essentially it's a rotation. SU3 stands for special unitary group. So unitary stands for kind of like, it's like orthogonal, but in a complex vector space. So this one has a three-dimensional complex representation. This one has three-dimensional real representation. So it's a real vector space representation. And this one has three-dimensional complex representation. This group is extremely important in quantum physics. I talked about this in my master class, that physicists like Murray Gell-Mann and others used representations of this group to predict the existence of quarks, the little particles which are constituents of the proton, neutron, and other particles which had been thought previously to be elementary, indivisible, and he showed. Gell-Mann showed that predicted that there are smaller particles called quarks. And for example, proton consists of 3 quarks, neutron consists of 3 quarks, some other particles consist of 2 quarks, and so on. This all relies on the representation theory of SU3. And how did he guess? Because he looked at a representation of SU3, and there is three-dimensional representation. In fact, complex, but now it's complex. So it's like you replace real numbers by complex numbers, okay? In fact, there are two different, distinct representations which correspond to 3 quarks and 3 antiquarks. But in addition, there are other representations, and especially there are representations of dimension 8, okay, dimension 10. And so the first discovery was that he was able, Gell-Mann and also Yuval Ne'eman and other physicists were able to group elementary particles into families of 8 and 10. And they actually mathematically correspond to representations of this group as U3, 8-dimensional and 10-dimensional. Interesting thing is that there is no 7-dimensional representation, for example. So that's why you don't observe any, groups of 7. Or there's no 9-dimensional, there's no 11-dimensional, so on. So you see these weird dimensions which suddenly pop up, as dimensions of representations. I should say irreducible representations. The point is that, of course, if you have one representation, one vector space, and you have another representation, another one, you can kind of put them together, take the sum. Mathematicians call it direct sum, and then dimensions will add up. So, but it's not very interesting. You can always add a trivial one-dimensional representation and therefore increase dimension by 1. It's not very interesting. What you care about is really the so-called irreducible representations. And so you got yourself 8-dimensional representation, 10-dimensional representation, and so on. And these numbers kind of look almost random, like why is it 8, why is it 10? It's kind of mysterious in a way, I should say, It's a little bit mysterious. But this is what representation theory is about. And so going back to Michael's question, so what are the open questions? What are the open questions in representation theory? To classify, for example, all possible irreducible representations of a particular group. So here we discussed the circle group, SO3, SU3. These are the first examples of what's called Lie groups. Lie groups are groups which kind of have a nice geometric structure. For example, a circle group has a nice structure. The set of points of the group is itself a circle, which is, what we call a manifold. So it's kind of a nice geometric shape. Likewise for SO3, SU3, even though those have higher dimensions. But these are the first and simplest examples of Lie groups, of the so-called compact Lie groups. So compact Lie groups, representations of compact Lie groups were already classified in the middle of the 20th century. And especially Hermann Weyl was very instrumental, mathematical physicist Hermann Weyl was instrumental in doing this classification. But then there are other kinds of groups for which much less is known. One example of a group for which less is known is a group of like SL2R. So this is another example. And this is a group of 2x2 matrices, really. It's 2x2 matrices. Can you see? I guess, yeah. With determinant 1, real entries, and determinant 1, AD minus BC equals 1. And so this is a so-called real group. It's not compact. And for non-compact groups, so non-compact means that it's sort of like it's not a finite shape. It goes to infinity. So SL2R has sort of infinite directions. You see. And so for non-compact groups, the classification is more complicated. For SL2R, we know. But for general real groups, for example, we don't know every detail. However, there is some new work now, and this is closely connected to the Langlands correspondence, to the Langlands program. So there are some ideas now actually coming from geometric Langlands correspondence. In other words, kind of a different, in my book, I talk about this sort of Rosetta Stone of mathematics, where there are different areas of mathematics which seem to be very far away, but the theory develops kind of on parallel tracks in those domains. There's some analogies, deep analogies between them. And so the geometric theory actually has to do with Riemann surfaces, and symmetry is connected to Riemann surfaces. But in fact, one of the applications of those insights which come from this particular part of the Langlands program actually shed light on representations of real groups. So this, I would say, is some very interesting work in this direction. Okay, let's see what else we got. Let me check my Twitter. Let me see if there is. Well, there's some nice comments here on my Twitter, by the way. So you feel free to send me tweets also at Frenkel. My handle is @Frenkel. But no questions through Twitter though. So let's see. Let me look at some of the other questions I have here. So. It's kind of weird because I don't hear anybody, I don't see anybody, so it's kind of like goes one way. So I guess everything is going well because, here's another one. Sergey asked, do you think our physical reality could ever be reduced to a mathematical model or computational code? Very good question, Sergey. I guess another Russian, my compatriot. As you might know, I grew up in Russia, so I came to the United States when I was 21, and so it sounds like by the name sounds Russian or Ukrainian, perhaps, I don't know. So from the former Soviet Union, let's just say, to be politically correct. So this is a very good question, very important question, because I think today we have a lot of discussions of that nature, we talk about things like artificial intelligence. Will we ever be replaced by robots, by computers? And some people even have ideas that, one day perhaps we will be able to upload ourselves into a machine and so on. And so there are many aspects which are very important here, I think. But I would like to start with something very simple, very basic. As a mathematician, I ask myself, what kind of questions can actually be represented in terms of numbers? So in other words, computational code. So I like the way Sergey put it. So he says reducing something to computational code. So what is computational code? Ultimately, computational code is a binary code, right? So it's a sequence of numbers, right? And so the question I ask myself as a mathematician, what kind of things can actually be done? To what things can we actually do justice by numbers? So we can completely replace by numbers. And what I find actually is very easy to find immediately sort of very elementary examples in which you can see rather clearly that numerical representation, yes, it's useful, yes, we can do it, but it doesn't really do justice to the object itself. It depends on a lot of other things. And any representation, numerical representation of even a basic mathematical object is actually reduction. There is a loss of information. So we cannot really speak of an equivalence, of a kind of identity between the object itself on one side and its numerical representation. And let me explain this in a little bit more concrete terms, and you will see what I mean. Okay, so let me erase. We just talked about vector spaces. It's actually a great setup for this. So let me maybe do like this, so you can see more clearly. So we talk about vector spaces, and this whiteboard, if you think of it as sort of extending it to infinity in all directions, it could be thought of as a vector space, as a two-dimensional vector space. Okay. For that, we actually need one more thing. We need to fix the origin, the zero, sort of the 0 point. Okay, the initial point, and just as our previous discussion. And then, what are the vectors in this on this plane? The vector can be obtained in the following way: we just pick another point, and then we can draw a kind of a pointed interval, a directed interval connecting the origin and this point. So this is one possible vector. So here is another one. Here is another vector. Okay, and there's actually more. So it's not just a static thing that, okay, so here's one vector, here's another vector. There is more, because what we can do, we can add vectors together, you see. So there is a so-called parallelogram rule. We can add vectors together. So we can draw from here kind of a parallel line like this, and we can draw from here a parallel line like this. Okay, and then with the connect the resulting point to the origin. So if this vector is called, we call this one V, vector V, and this one W, and this is V plus W, right? We can also multiply vectors by numbers. For example, 2V would be a vector with length twice the length of V, pointing in the same direction, and so on. So they have these vectors, they live here on this plane, and they have a very rich life. You know, we can add two vectors to each other, we can multiply vectors by scalars, and so on. And then a mathematician comes in, and a mathematician says, you know what, I would like to put a coordinate system here. I would like to put a coordinate system, which is actually a good idea. It's a very clever idea. So for example, I can draw a coordinate system. I draw two coordinate axes. Here is one, and here is another one. So, well, I also have arrows here and here, but they have a different meaning. It just points in the positive direction for the axes. Okay, so two axes. X and Y. Usually we call them X and Y, right? Okay, so if I do that, then actually I can represent my vector by its coordinates, because the end point of the vector can be represented by two coordinates. Namely, I drop a perpendicular on this line, right? So I get some coordinate X. So let's say, just for to be concrete, let's suppose I get some number 2. Let's say that this is 1, 2, so 3, 4, and so on. So, and likewise along this one, it would be this, 1, 2, 3, 4. So using this coordinate system is really like a coordinate grid, because I can also draw. I'm not going to do it so not to mess up my picture, but think of it as you can draw all these parallel lines and you kind of get like a coordinate grid. You impose the coordinate grid onto this vector space. And if you do that, you can also draw the perpendicular onto the y line. And so you see, it has an x coordinate 2, it has y coordinate 3. So then we can represent it by these 2 points, 2, 3. Right? And this is a numerical representation of this vector relative to this coordinate system. Sometimes people write it as 2, 3 using this notation. It doesn't matter. And then once you do it, it's very convenient because every vector can then be represented like this. So for example, this one would be something like 1 and 3, 3 and 1, right? And so on, right? Every vector. And for the operation of addition and scalar multiplication then becomes very concrete, can be expressed in terms of those numbers. And when you do that, and if you're a mathematician, you just love it because it gives you such a really efficient way to deal with these vectors, to many questions related to these vectors. And then you kind of, it's very natural, it's very tempting to kind of forget that there is a difference between the two things. And you kind of then feel tempted to say that this is a vector, 2, 3 is a vector, 3, 1 is a vector. But that's not really true now, is it? Here's a vector. Here's a vector. It's something live, it's something living on this. It's almost like a living organism on this plane, metaphorically speaking. Whereas this is just 2 numbers, right? It's 2 numbers. These 2 numbers are not the same as this. Now, let's remember how we got those numbers. We imposed something onto this plane. You see, this vector lived here, so to speak, on my whiteboard. Even when I go home to sleep at night, it will still be here, right? It doesn't depend on what I think about it. It doesn't depend on what coordinate system I impose on this plane, right? It's here. I imposed this coordinate system, and then once I imposed this coordinate system, I was able to convert this vector into a pair of numbers. But this vector itself is not a pair of numbers. And you can see it very clearly. If you realize that someone else can come into my office, no one is going to come because I should put a sign that it's live, live sessions and not disturb. But if someone else would come, they could actually introduce a different coordinate system. It could be tilted, right? And who's to say whose coordinate system is better? All coordinate systems, in fact, are valid. And in fact, when you study linear algebra, you realize that it's not even necessary to have these lines to be perpendicular to each other. Any sort of transversal lines will do as the coordinate axis, you see. So there are infinitely many coordinate systems, infinitely many choices for a coordinate system. And every choice, once you make a particular choice, this same vector will be represented by a different pair of numbers. It's not attached to this particular pair of numbers. It can be represented by a different pair of numbers. So you see that there is a difference. You see, there is a difference between these objects like vectors, and you can find many examples of that, similar examples. I'm giving the most elementary example, but there are many other examples like that, where you have a mathematical object, like a vector, which you may be able to represent by a pair of numbers. But this pair of numbers is not the same. It's a particular projection, if you will. I mean, here is maybe a way to think about it. Like look at this cup. Look at this cup. I can consider its projection onto the floor. And if I look at the projection of this cup onto the floor, what am I going to see? I'm going to see a disk. Well, there will be like a little thingy protruding from it, which corresponds because of the handle. Okay, so it will be a disk. But if I project it onto this whiteboard, I will see a rectangle. So now, what is this object? Somebody will say, well, it's a disk, because that's what I see when I look on the floor. Well, that's not the disk. Somebody else will see, well, I see this. I see a rectangle. Is it a rectangle? No. Then somebody really clever will come and say, actually, it's both. It's a disk and a rectangle. Well, but that's not that either. This is something totally different. It's a three-dimensional object. And we are talking about it in terms of projections, which are two-dimensional. So it is something else. And likewise, this vector is not this pair of numbers, is not this pair of numbers, is not another pair of numbers that you can derive by using a particular coordinate system. It is something else. Numbers appear when we represent And we can represent it in many different ways. So it involves a choice. It involves a choice. I make this choice. It is sort of my choice. I can actually change. I can make a different choice tomorrow, right? The vector will still be there. If the vector could speak, you know, and we ask him, what are the pair of numbers? What are your pair of numbers that, you know, that represent you? The vector will be like, what? What are you talking about? What are you talking about? What numbers? I don't know anything about numbers. The vector couldn't care less about numbers. You see, it's just there. It's just there. It's our choice. It's our free will, you know, if you like, to choose those coordinates and to represent. And it's very useful. I'm not saying it's not useful. It's very useful because you see, when the vector is drawn like an arrow, it's not very functional. You can't do. It's not so easy to do calculations with it. When you convert a vector into numbers like this, then you can do calculations, you can program, and so on. That's incredibly useful. What is not useful is to forget the difference between the two. And if you are a mathematician, if you know linear algebra, you see immediately the difference. I'm teaching a linear algebra course. Maybe that's why I'm sort of like passionate about it right now, because I was just teaching that to my students at Berkeley about a month ago. And I was explaining to them that there is no canonical, there is no preferred choice of coordinate system, or we call it basis. There is no basis, because you can think of, you know, choosing coordinate system as a choice of a basis. There is no canonical basis. There is no preferred basis in the two-dimensional space. Therefore, there is no particular pair of numbers representing this vector. I will tell you more. Any pair of numbers will represent this one vector. You can always find a coordinate system in which any given pair of numbers will represent this vector. So how can you possibly say that this pair of numbers is the same as a vector? That's not true. And if it's not true for a vector, then I'm sorry, but how can it be true for a human? How can it be true for life? How can it be true for things which are going on around us? The so-called reality. Yes, we can have projections of that reality. Yes, we go to movies, right? We go to movies and we watch and we laugh and we cry, you know, and we are, you know, very much get involved in this story and so on, right? But we know that it's a projection of reality. It's a particular representation of reality. Nobody would say that the movie is the same thing as what we experience in our, you know, it's connected, but it's not exactly the same as what we experience in our life. And so this gives me pause when I hear people like Ray Kurzweil and other self-appointed, you know, singularity prophets who are telling us that there is, you know, one day there will be computers which will be able to replace us, and all we'll need to do is to somehow upload ourselves onto those machines. Because when they say that, it seems to me they are assuming that they are nothing but machines. But what is a machine? What is a computer? A computer is an algorithm. And as Sergey said, you know, it's computational code, a sequence of zeros and ones. So when somebody like Ray Kurzweil says, you know, singularity is coming, what he's saying is that he thinks he's nothing but a sequence of zeros and ones. And what I'm telling you is, if you learn linear algebra, you understand very clearly that even a vector is much more than a sequence of zeros and ones. And so are we, much more than a sequence of zeros and ones. Now we have to study numerical representations, we have to use them. But we go astray, we really go astray when we start forgetting where those numbers come from. They come because we make a choice of a basis, for example, in this case. And that involves our choice that we make. All right, so I hope I give you some ideas on this. Okay, let's see. Ashish asked me, do you think mathematics is an invention or a discovery? Why is it so useful in describing our natural world? Thank you very much, Ashish. This is a great question. And I talked a little bit about it in my masterclass. I talk a little more about this at the end of my book, Love and Math. But let me tell you what I think. I think it's a very deep question, very important, and we kind of don't. Even we mathematicians, we don't talk about it enough, because I think it's a very important issue. And I honestly didn't really think much about it myself before I started writing my book. And when I was writing my book, I really thought, okay, well, I should understand it, but I should figure it out myself. Like, what is it? What are we doing? What are we doing, mathematicians? Are we inventing this stuff? Are we inventing all of this? Or is somehow this stuff already exists somewhere and we're just connecting to this sort of hidden reality and we are discovering it, And so I think roughly speaking, I think it's very complicated. It's not something which can be explained in one sentence. But the very rough answer is I do believe that we discover mathematics rather than invent. And what makes me think so is that the kind of universality of mathematics, that the fact that it is so unchanging and through time and space. In other words, Pythagoras, discovered his theorem, Pythagoras' theorem, just as an example, 2,500 years ago. In fact, it was even discovered before him, which only proves my point, because it has been discovered by many and is still being rediscovered in classrooms around the world. When you study it for the first time, it's almost like you feel it finally clicks and you understand what it says. It's almost like you yourself have discovered it anew, right? But we all discovered the same thing. X squared plus y squared equals z squared. If you have a triangle with a right angle, and you have x, y, and z, we write x squared plus y squared equals z squared, right? So now, I guess we will all agree that we're not going to say tomorrow x squared plus y squared equals z cubed, right? I mean, that just sounds absurd. X squared plus y squared will be z squared for any triangle with a right angle today and 1,000 years from now, as it was 2,500 years ago when Pythagoras came up with this, and even earlier when mathematicians in other civilizations discovered the same fact. So this is quite different, you see. This is quite different from, for example, even from physics, because obviously in physics, you had in the 18th century, you had Newtonian mechanics, which was particular way to describe the world, was a particular mathematical theory to describe the motion of different objects and so on. And so Einstein showed that was not correct, right? So for example, this separation between time and space, that space is absolute and somehow time can be separated from space. We just know for a fact. There are experiments. There have been experiments set up, very, very precise experiments, which show that that's just not the case. Einstein's relativity turned it upside down. And so the theory had to be updated. So right now, for example, now we have special relativity, we have general relativity. But it's clear it wouldn't be surprising if, 20 years from now, 50 years from now, 100 years from now, somebody will append Einstein's equation. Somebody will update Einstein's equations. Perhaps one of the viewers of today's live session will say something totally different and say, look, actually, the truth is much more sophisticated, much more complicated. So there are updates, physical theories, as well as theories, other scientific theories, get updated. But mathematical facts, once they're established, they don't get updated, like Pythagoras' theorem. So what does it mean? That there's something very special about mathematics, and we don't really fully understand it. We don't fully understand it. But I find it very hard to believe that we somehow invented, because who invented this? Who? Pythagoras? Well, you should then talk to mathematicians, in China and in other. I think it was also in Babylon where they came up with this. We have evidence that they came up with the same ideas before. So they invented before Pythagoras. Okay. What about a kid in Manhattan who invented it yesterday? He invented it as well. And how come we all invent the same thing? Do we have some kind of a telepathy between each other? That somehow we're communicating this to each other? Somehow, when I talk about these issues, people dismiss this idea that mathematics exists outside of space and time as a kind of a special reality to which we connect somehow. Now, we don't know how, I don't know how, but people kind of feel very uncomfortable about this because they say it sounds mystical and it sounds kind of crazy. But what people don't realize, that if we take the opposite point of view, if we take the point of view that actually we are inventing this stuff, I'm sorry, but it sounds even more crazy because that actually means that we are somehow communicating to each other. How else? Why are we synchronizing our mathematics in this way? We don't speak the same language, right? We speak different languages. People say, well, but mathematics is a language, and so it's kind of like a language. So we just do this, so that's why it's the same. But I'm sorry, you know how many languages there are on the planet Earth today? I don't, but I'm sure that more than one. Okay, I can tell you that, more than one. And there is only one mathematics, nonetheless. Now, there are some subtle issues, but somebody might raise an objection to this and say, look, actually, there is some dependence on axioms. And for example, even in set theory, there are some disagreements. What is the correct system of axioms? Right? So we have a famous system of axioms called Zermelo-Frenkel. Not me, unfortunately, somebody else with the same last name, spelled slightly differently. Zermelo-Frenkel. But then there is axiom of choice, right? And then there is a continuum hypothesis, which is not cannot be proved within those axioms and so on. So there are some subtle issues about axioms, but it's kind of the next level. So I don't, even if there is this issue of, because you see, the point is, no matter which axiom system you will choose, what I'm saying is that once you choose the axioms, the system of axioms, once you choose that system of axioms, all the mathematical truths will be the same for everybody. So yes, maybe you do have a choice of how you choose the axioms, but it's still, the issue remains. Why is it that within a particular system of axioms, there is no, we have no, it's not subjective, it's objective knowledge, which is independent of the observer. So, you know, in my book, I talk about, in this context, I talk about Évariste Galois, the great, you know, French prodigy who came up with the ideas of symmetries and number theory. And, you know, he actually was killed in a duel when he was 20 years old. And he was writing his work, you know, the night before, finishing some of his works the night before the duel. And so it's kind of, I really kind of, I'm kind of really find it striking, this image of this young man, you know, sort of like writing a love letter to humanity. It's almost like, you know, he's not writing a poem, a love poem to his lover. He's writing a mathematical formulas, and that's his sort of love letter to humanity. So it's really beautiful. And but what if, you know, what if those papers were lost? I mean, it's possible. What if there was a fire and all of that would be lost? So should we think that somehow somebody else would come up with something totally different? Was he inventing the stuff? If he was inventing the stuff, how come 40 years later, 50 years later, people came up with exactly the same ideas? You see, so there is something very special about mathematics, and we should not so easily dismiss just because it sounds spooky to assume, to imagine that there is some mathematical reality somewhere. You know, because we know that there are some spooky things which are actually true. You know, Einstein talked about, it's a separate issue, but since I used the word spooky, I might as well talk about this. You know, spooky action at a distance. We talked about entanglement. Einstein, Rosen-Podolsky experiment that he proposed, a thought experiment, which he thought would show that quantum mechanics is absurd because it would show the spooky action at the distance. And guess what? Einstein was wrong. You know, like every human, a great genius can also be wrong sometimes. And so he was wrong. So spookiness doesn't mean it's not real. We have been shown time and time again how spooky things actually are real. And likewise, it may appear spooky to imagine that mathematics somehow exists outside of reality. But we should not dismiss it. Rather, we should think about it. What does it mean? What does it mean? What can we learn from this? What are the other possibilities? I should warn you, though, that some mathematicians take it to extreme. And even physicists. I will not mention any names, but some of you perhaps know who I'm talking about. And some people go too far and really do a disservice, I think, to mathematics and physics and science when they say that actually there is nothing but mathematics. So they understand this fact that mathematics exists outside. And actually most mathematicians, if you really press them hard, they will admit it. They will admit it to you privately, but people are afraid to talk about it because it sounds kind of crazy. Sounds spooky. I understand that. But the danger is to realize that and then to convince yourself that actually there is nothing else, that the world is mathematics. And this is what I was talking about answering earlier question of Sergey, where he asked me, is it possible that our reality is just a computer simulation or something like this? This is what these people are saying to us. And they kind of say, well, we are mathematicians and that's what we know mathematics and that's what it tells us. No, it doesn't. I'm sorry, but it doesn't. I'm a mathematician. I know that. I do believe that mathematics exists outside of space and time. It presents a kind of a, Platonic reality, if you will. So let's refer to authorities, Plato. I mean, let's refer to some authorities, Plato or something. But it's just a label. Platonism, not Platonism. It doesn't matter. The question exists, with or without Plato. Did Plato invent this question or discover it? That's another interesting question. But yes, I do believe that. I do believe that mathematics exists outside. It is, as I say in my book, a kind of a hidden reality. But I do know that that's not everything. And I just showed you a very simple example of where we can, things are not so simple, you see. So I think we should think about it more, and we should approach it with a sort of an open mind, And another alternative people suggest sometimes is they say, well, mathematics is just like a game of chess. It's like a game of chess. So you just write some rules, and then you just kind of like throw the dice, No. First of all, Gödel's incompleteness theorem, which I talked about earlier, puts a big dent in this kind of argument, because we know that not all mathematical truths can be obtained within a fixed formal system. There will be statements which cannot be proved within this formal system. This is answering the question earlier. I said that, right? So that to me is an indication. It doesn't prove anything. It doesn't prove this kind of discussion. It's not a kind of discussion where I can formulate a theorem and prove it for you. But it's an indication. It's an indication that that's not the case. Number one. Number two, what about, game of chess? I'm sorry, but it has not been useful in our physical theories. A game of chess is a lot of fun. We play chess, we enjoy it, but it doesn't help us in understanding the world, and mathematics does. And so, we're going back to Eugene Wigner's famous line that unreasonable effectiveness of mathematics. And in fact, Ashish, in his second part of his question, he asked me about this. Why is it so useful? So this, I think, is a mystery. It really is a mystery. In other words, what it seems is that this hidden reality of mathematics is really intricately connected with our physical world. I mean, it's not really. In some sense, you would think that that's a good thing. So it's not just completely separate from it, but mathematics connects to the physical world in very unexpected, strange, and surprising ways. For example, complex numbers. Complex numbers, mathematicians struggled with this idea. What is the square root of -1? It doesn't exist. We should ban square root of -1. Then they realized, that square root of -1, what we call I, actually is a meaningful number, and we can create meaningful numerical systems and work with them and so on. But little did mathematicians know that this would become bread and butter of quantum physics. It's absolutely essential, because the phase factor of, as you may know, in quantum mechanics, of the wave function is incredibly important. That's why we can have interference between different particles, like double slit experiment and so on. This is explained precisely by the fact that the wave function is complex valued. It's not real valued. It's only when we take the square of the absolute value of the we get the probabilities, the so-called Born rule and so on. But the wave function is complex valued. When mathematicians came up with complex numbers, could they possibly guess that this would become an essential ingredient in description of nature? Of course not. And yet it happened. So you see, it's a very, very subtle interplay between mathematics and physics. And we should not pretend that we know why it happens. We should not pretend, because nobody knows. So this is a question for us, and this is great. It's one of those things that are still open, and some of those things that we should think about. So I think it's great that there are such big questions that we still have. All right, one more question. Let's see. We are kind of close to the end. Eric asks, do you think the Langlands program relates to other major unsolved problems in mathematics, such as the Riemann hypothesis or P versus NP? Very good point. So, I sometimes say, kind of a little bit tongue-in-cheek, I sometimes say the Langlands program is kind of like a grand unified theory of mathematics. I guess, we mathematicians kind of like have an envy, a grand unified theory envy. Towards physicists, because physicists always talk about TOE, theory of everything, grand unified theory. So I thought, what about us? What about us? Mathematicians, we also want a grand unified theory. Physicists got so many, and we know how well that has worked out for them so far. So I kind of joke about it. I say, the Langlands program is a grand unified theory of mathematics. I don't mean it seriously in the sense that somehow there's one theory which encompasses everything. No, that's not possible. And this is good also because mathematics is just so big and so multifaceted that you don't expect sort of one formula to explain it all. By the way, I don't believe that one formula will eventually explain all of physics either. I don't believe that either. Or that you can write it on a t-shirt or something, somehow, all of physics. I don't believe that either. But with mathematics, for sure, that's not the case. And so when I say it's a grand unified theory, I mean that it actually connects many different subjects and in unexpected ways. But there are other theories of that kind. So Eric is asking, well, can it actually shed light on some concrete problems? Well, so far, first of all, I would like to say that it has already shed light on some big, long-standing problems. One of which, of course, is Fermat's last theorem. Right? So Fermat's last theorem is definitely the proof of Fermat's last theorem relied on a result which is squarely within the context of the Langlands program, even though it was proposed originally by other mathematicians, by Shimura, Tanyama, and Wei, right? And so, but it is really a special case of the Langlands program. And so, but Riemann hypothesis, I think, is very closely related to the kind of things that we do in the Langlands program. In the classification which I talk about in my book and which I mentioned also in my masterclass, sort of like in the number theory column of that. And in the second column, in the column which connects to curves over finite fields, the Riemann hypothesis, an analog of Riemann hypothesis, is known as the Wei conjectures. And the Wei conjectures were proved, of course, by several people, including Grothendieck and the great French mathematician, and Pierre Deligne, who was a professor at the Institute for Advanced Study. So this work is actually very closely related to the geometric Langlands correspondence. And so I have hope that the ideas of Langlands program may very well one day shed light on the Riemann hypothesis, could be very useful. In some sense, it's already happening because, I mean, one of the reasons why André Wei came up with this Rosetta Stone and so on is because he wanted to understand Riemann hypothesis. So what he did is he reformulated Riemann hypothesis, which originally appears in number theory, in a different area of mathematics, what I call, study of curves over finite fields, where actually it turned out to be easier to handle and to prove. And then once you prove it in that domain, then you kind of hope that, well, perhaps it can shed light on a regional problem, right? So in some sense, it's already happening because the Langlands program is very much within that framework, that Rosetta Stone of André Wei. But so that's one thing. As for N versus NP, I'm not sure. I don't know. I mean, I would not be surprised. But it kind of P versus NP lives in a kind of a different continent. That's what it appears today. Kind of lives in a different continent of mathematics. But Langlands has taught us that those continents actually may well be connected. May well be much closer to each other than than it looks at first glance, right? And so. So why not? I wouldn't be surprised. I don't see today. I'm not aware of any particular developments which would link the Langlands program to N versus NP, which of course is an incredibly important problem. But who knows? I mean, who knows? Because, for example, it could be that somebody, let's say, if you want to disprove it, you could come up with some problem which is one but not the other, and then maybe such a problem. And in fact, I'm looking here at the list of questions, and Isa also asked me. It's very closely related. So, does the Langlands program search for symmetry in mathematical? Does Langlands program search for symmetry in mathematical logic, as well as the so-called continents of mathematics, which I like to speak about these continents. For me, mathematical logic is one of the continents. In some sense, mathematical logic is even more, because mathematical logic is kind of the foundation of all of mathematics, right? And as I said at the very beginning of this broadcast, I kind of feel that we, professional mathematicians, we don't pay enough attention to mathematical logic and to issues like Gödel's incompleteness and the fact that, we still don't have a settled system of axioms for set theory and so on. I think these are very, very deep questions. So far, as far as I know, the Langlands program has not shed light on that, on that circle of questions, but has not yet shed light on those kind of questions. But who knows? It may very well be. One thing I'll say for sure: the ideas of symmetry are definitely fundamental to mathematics as well as physics, right? So we know that. We know that very well, that symmetries are fundamental. And so since the Langlands program has its roots really in the study of symmetries, I would say that in some sense it kind of like, you cannot really separate the Langlands program from the study of symmetries. And therefore, I wouldn't be surprised if methods of group theory and so on would be used more and more in the coming years in mathematical logic. There is one aspect of this, which something that's already happening. There is a so-called model theory, which is kind of an offshoot of mathematical logic. One could probably say it is part of mathematical logic, which has benefited. This subject has benefited lately from some ideas in other fields of mathematics. And in fact, methods of model theory, conversely, have been used to give proofs to some long-standing problems like Lang's conjecture and so on in algebraic geometry. So in other words, some bridges are already being built between mathematical logic and kind of, should I say, mainstream mathematics. Well, I hope my friends logicians will not be offended by this, because my point is exactly that mathematical logic should become more mainstream in some sense, that we should pay more attention and we should really kind of make it bring it more to the forefront of mathematical research. So in that sense, I think it's a very positive development, because when something like this happens, when you are, you have a long-standing problem in algebraic geometry, which you cannot prove, you are unable to prove for many years by using methods of your subject, and then suddenly logicians come and using some methods in model theory and so on, help you solve that problem. That's an indication that perhaps algebraic geometers should learn more mathematical logic, maybe conversely, right? So that it's, again, this bridge is kind of being built between those subjects. And that, I think, is very important, because each time you connect these different parts of mathematics, you see, you are actually showing the unity of the subject. And in the beginning of my masterclass, I talked about this question whether aliens, if we ever meet aliens, would they have the same mathematics as we do, right? So would they have the same mathematics as we do? And I believe that there is only one mathematics. But it's possible that they would know a particular part of mathematics, which we don't know, maybe. And we know some other part. And so then the question will be kind of connecting the two. And so kind of expanding, like a jigsaw puzzle. So they solve part of the jigsaw puzzle, we solve another part of the jigsaw puzzle, but we can put them together. But you see, this, if you believe that, if that's what you believe, then you realize how important it is, at least even before we meet any aliens. We should not consider mathematicians in another subject of mathematics living with us today as aliens. And we should rather try to unify mathematics as much as possible. And we should try to find common ideas, common language between those parts of mathematics which we know today. Because if we ever have a chance to communicate with aliens, and for sure we should at least, communicate with each other for the benefit of the subject as well as for the benefit of other areas of science. So we are kind of running a little bit over time, and I could go on for much longer, but the good people at the World Science University who have facilitated this, and I would like to thank them for, first of all, doing such a great job putting together the master class. I got a lot of positive feedback from many of you on that, and I cannot really take credit for it because I just went and I spoke and I answered questions and so on. It's really the good people of the World Science University that are sort of unsung heroes of this, that they have done such a fantastic job, such great quality, putting all of this together. And then organizing this live session, which has been a lot of fun, for me, at least. I hope you enjoyed it. And thank you so much again for sending such great questions, stimulating questions, because, you may think that I already know all these answers, so I'm just sitting here and trying to explain something to you, to teach you something. But, it's not like that. It goes both ways. Every time I try to explain something to you, I'm also learning. I'm also learning. So it was very useful for me as well, this interaction. And I apologize to those whose questions I have not answered. I think I answered more or less the most important ones. But if I didn't have a chance to answer your question, and you would really like to get the answer, here's what I suggest. Go to my website, which is www.edwardfrenkel.com, www.edwardfrenkel.com, and then there is a easy way to contact me through that website, and just send me your question, and then I will just answer it by email. How about that? All right. So I think it's time to end this hour discussion, and I want to thank every one of you for tuning in, for sending your questions, and have a great weekend. And I hope to see you all soon.